Welcome to number 6 on interference, further evidence of the wave model of light. And what I've pre-drawn is a very crude version of Young's famous experiment where there is a light, and he did this in dark because the time he did it there was no good way to have a light-proof area. So he had a light, 2 narrow vertical slits, and some distance away, like a metre or more, he had a screen, which in this case was a photographic plate, and on that he found a whole series of vertical lines, and we call those vertical lines fringes. No idea why they're called fringes, just the term they've been used. So let's talk about Thomas Young. In 1803, Thomas Young performed his famous experiment. He used a closed box at night to send light through 2 vertical slits and produced a regular pattern on a photographic plate. Okay. So, a regular pattern on a photographic plate. Okay. This occurred because each slit acts as a new source. Huygens principle, that is. Okay, an attempt to draw that, because I'm doing this one live instead of preloading the diagram. Here's hoping. This time this is the barrier. We are sending parallel wave fronts into the barrier, and you'll get a chance to experience this in class. So these waves are heading towards the barrier, and each slit acts as a new source. My task is to try to draw these as regular as possible. Try them around this one. I think if I stop there I should just be satisfied that it kind of looks correct, because what we have coming up the middle looks like a central maximum, and that is fantastic. And coming out here and here, which didn't work as well on that side, is maximum 1, and on the other side there'll also be maximum 1, but in class we'll have a look at some really correct diagrams that are easier to follow. like when we did it with the springs, the dead bits in between are called nodes, but they're not as easy to see on this. But the bits in between are nodes. That's where it's nice and quiet or still, depending on what sort of thing you're generating the waves with, whether it's water or sound or whichever. Okay. There is always a central maximum. On the central maximum, there is no path difference. Now, what does path difference mean? It means the distance to each source from any point. Now, the sources, of course, are the slits, because each slit acts as a new source. So, the central maximum is called constructive interference. Okay. We will squeeze in a little bit more on this page. The next maxima occurs when one source is exactly one wavelength further away, because this means the waves match again. And reinforce. Okay, which is, of course, another name for constructive interference. Okay, moving on. Again. Okay, so between the maxima are nodal lines. So points of cancellation. So these are quiet points, dark points, depending on what you are using. So there could be quiet points, dark points, still points, depends on the type of waves. And this is called destructive interference. Now, what does that mean in terms of sine waves coming from something? It means if you've got one sine wave happily coming from the first source, but from S2 you're at a distance, so that, if I can manage to draw it correctly, and when you add them together, you get nothing. So the nodal lines occur with path differences of half lambda, 1.5 lambda, 2.5 lambda, etc. So n minus a half lambda is the path difference, where n is the nodal line. And we'll get to all of that in a minute about what nodal lines and so on mean. So due to loss of intensity due to distance, the maxima further away from the centre are a little bit duller or less bright or quieter, depending on what sort of waves you're using. So the ones away from the centre are less bright, okay, and that's just due to distance. There's nothing special about it. You're further away from something, it's less bright. Okay, path differences. And what that actually means. So let's draw it a completely different way. S1, S2. So the two sources. We won't try drawing all the waves. We'll just try drawing a dotted line over to the screen where we're detecting things. Central maxima, max 1, other side, max 1, further down, max 2, further up, max 2, and in between, N1, N1, N2, N2. We should get nodal lines that match on both sides as well. Let's do what path difference actually means, because it does mean a physical difference in path. So we'll do the path to the max 1. D1, D2. So distances from the two sources. That's what path difference means. Nothing complicated, nothing weird, it just means a physical difference. So path difference for maxima. Okay, so we're doing it to M1. So the path difference which is D1 take away D2 equals lambda. Now, to generalize it, that means it's n lambda, always a whole number, wrote that really badly, n lambda, always a whole number of wavelengths, because that way the waves match exactly again. And don't forget, for nodes, path difference equals n minus a half lambda. Always a multiple of half a lambda. That way you get cancellation because one wave is going up while one wave is going down. Fringe separation. That is, how far apart the maxima. So, distance between maxima. That's what fringe separation means. So, fringe separation, delta x equals lambda L on D, where delta x, fringe separation, and obviously meters, lambda equals wavelength, meters, L equals distance to the screen, whoops, meters, and D equals separation of slit centres. You don't have to memorise this formula. It's on your formula sheet. You can write it on your own sheet. You just have to be able to interpret the trends. That's what's important about this and many other things that we do. I'll just bring that up onto the screen to finish off. So all we have to do is be able to interpret the trends, it's not a memory test. Okay? So what we'll do next week is we'll demonstrate this as well. So we'll demonstrate interference in the class with sound, so you'll be able to experience it physically. And hopefully we'll be able to understand it, because this is one of the areas that was done badly on last year's exam. I'd love it to be one of the areas that we do really well.